this segment will talk about the solutions to our separated equations, and we'll rely heavily on some work that you've previously done. One of the equations in our separation of variables was this one. This was the angular part for the function g of theta and phi. And remember, there was a separation constant. And if you go back and look, you've actually solved this one before in your quantum mechanical solution for a rigid rotator. So the quantum mechanical rotator problem. And what you found there, or should have found there, is that for this to have acceptable solutions, namely normalizable, the wave functions have to be normalizable, and for this to lead to normalizable wave functions, I can't have any possible separation constant here, but only a discrete set, although there's an infinite number of them. This constant, separation constant, has to be of this form here, where L is 0, 1, 2, 3, etc., is any non-negative integer. And so one has to have that. And then also there was a degree of degeneracy of it, and you also had another set, M sub L, which is 0 plus or minus 1, plus or minus 2, all the way up to plus or minus L. So once you've got a particular L, then you can get the allowed M sub L's that will give normalizable solutions as well. And the solution, as you may remember, was the spherical harmonics. Now, actually, any constant times a spherical harmonic is also a solution of this equation, and but it's just says it's a linear equation. So sometimes people will put a constant in front of that. I'll just leave it off at this point. In any event, the solutions are these spherical harmonic functions, a special function of some note in a number of areas. So that differential equation for the angular part is simply this, and we have these values for L and M sub L. Some people like to, I usually like to write it in this fashion, but some people like to write this. You go from minus L up to L in integer steps, but I think this set and this set, I think you can see, are pretty much the same, or they are the same. And your book didn't seem to have, I couldn't find a spherical harmonics table anywhere in it, so I attached one here. This is one that I will sometimes pass out in a couple of different classes that I teach related to quantum mechanics to the physics guys and girls. But just the first few, and that's really about all that I ever deal with, is just some of these. This is kind of a nice table because it's tabulated by L, and it gives both the spherical version and the Cartesian version. You can make a transformation into the Cartesian system as well on these. So anyway, that problem you've solved. So. And if you remember, as part of that rigid rotator problem, you had some interpretations for these quantum numbers. L squared was the total angular momentum squared, and it was this quantity here. Same thing in this problem, except now the L is the orbital angular momentum of the electron as it orbits about the nucleus. And again, the square of the angular momentum cannot take any possible value, but is discretized. It's quantized into these steps where L can be 0, 1, 2, 3, etc. And likewise, the M sub L has the interpretation as being related to the Z component of the angular momentum. And likewise, this would be for inclined orbits, I guess. In a classical sense, but the quantum number here is M sub L, and L, the Z component of the angular momentum cannot take any possible value, but only the M sub L value, so it goes from minus L to plus L in integer steps is all that's allowed for it. So it's likewise quantized. Your textbook uses J's instead of what I'm calling script L, and they use capital M's for what I usually call M sub L. And so their notation, I think, for the spherical harmonics are these, and it matches up with the ones that are here. Well, we can do a similar kind of thing for the radial equation. So let's take a look at the radial equation. And so I pulled the radial equation from the previous segment on this. And this was the K over here. If you remember, the separation constant, K, occurred in both the radial and the angular equation. But K for the angular equation to have acceptable solutions has to be this particular number. So the first thing that you have to do is in the radial equation, substitute in for K that value for K that we got in the previous segment up above for the angular portion, minus that. And then that's equal to all of this, and then ultimately I divide through by the h bar squared 2m. This one didn't have an h bar squared 2m originally, so when I divided it, I get r squared over 2 mu, and then the h squared flips over on top. And then let's see what else. I multiplied through by minus 1, so minus 1 plus, minus 1 here, and plus as well. And then finally, I take this term over to this side. And ultimately, I get for the radial equation this rather formidable looking equation. In fact, it is tough to solve, much similar to the spherical harmonics that you got for the rigid rotator problem, and also a solution to this. The method that it takes to solve this is to use a method from differential equations called a series solution technique. So you look for a series solution. What you find is, in this series solution technique, that not every possible value of E is allowed, but only a discrete set. And it can only have normalizable wave functions or acceptable solutions, provided this energy is again discretized, it's quantized, and in this form, which may look familiar to you, but that is where n is the principal quantum number, and it has to be an integer 1, 2, 3, etc. And moreover, that for a given value of n, so give me an n, say 2, then L can only be, the L max can only be n minus 1 and lower. Yeah? And that gives us the radial wave functions R in L. I'm not going to go through it. The function that actually comes out of this is a Laguerre function, so-called Laguerre's equation. But in your textbook, table 13.3, which I reproduced, I think, yeah, I did, it lists a few of these wave functions. So for the n state and the L states, I noticed kind of interestingly, the author has reverted back to N and L. Really, I think to be consistent, he would need to write this as capital J and N and J here. But in any event, he has written out several of the lower N values. He's also matched them up to the spectroscopic notation, the 1s, 2s, 2p, etc. He does it by energy levels. So the principal quantum number N labels the energy level, and then the L gives you the angular momentum portion of it. Notice this rho is related to our R, the radial value, and what else is it here? The A naught is the Bohr radius, I think. So there's some. You have to have a dimensionless quantity up here in these exponents and then these squared terms, and so to produce that, that's what he does, and then uses the Bohr radius to simplify a lot of these expressions. So put all that together, the total solution is just R times G, and for us it becomes this. Usually you see it labeled, the wave function, with N, L, and M sub L. It's a function of R, theta, and phi. It's in spherical coordinates. And it's just the product of the solution to the radial equation and the solution to the angular equation. Again, some people will put a normalization constant up front, so sometimes the Schrodinger equation is a linear equation, so any constant times this is also a solution. Sometimes they will put a different constant out front, but I'll just leave it as one. In that, we found several curious facts, namely that energy is quantized in this form, where N is 1, 2, 3, 4, etc., for us to have an acceptable solution to the Schrodinger equation, one that vanishes at infinity and is square integrable, basically. And then one also has relationships on the angular momentum. The square of the angular momentum has to be this. L can take on any value. You give me an N, and then I get the maximum value of L. So if N were 3, then I'd plug 3 in here for N, and then L maximum goes up to 3, and then I would have 0, or N goes up to 3, so L goes up to 2. I would have possible values of 0, 1, and 2 when N is equal to 3. And then likewise, once I have a particular L value, maybe 1 here, for instance, then M sub L only goes from minus L up to L in integer steps. So if L were 1, I would only get 3 values here. I'd get minus 1, 0, and 1 for the 3 possible values. Well, that pretty much encapsulates what I'm going to say about the actual solution, and we'll be using that in what follows for some various approximations.